Okay, so now let's look at using the Bootstrap for something called bagging and something called random forests. So the term bagging comes from the full name, which is bootstrap aggregation. So we bootstrap the data set, we learn some model on each bootstrapped set, and then we aggregate the results to get one final prediction. That's called bagging. All right, so our algorithm is as follows. For little b equals 1 to capital B, where we decide what this capital B is, we first generate a bootstrap data set of the same size as our training data. So this data set is going to have repeats of certain data points, and some other data points are not going to be in that data set. We then learn a classifier or a regression model, FB, on the bootstrap data set. So we have capital B of these classifiers or regression models where each one is learned on a particular bootstrap data set. Then for a new point, x0, we want to come up with a prediction. And that prediction is simply the prediction that we would make, or the average of the prediction we would make for each individual bootstrap data set. So we evaluate the new point on the classifier or regression function learned for the bth bootstrap data set. We sum over all of them, and then we average. So for regression, this average would be the prediction. For classification, we can view each classifier is like giving its vote for what the class should be, and then we pick the majority. So when we want to bag trees, here's what we get. Imagine that we're doing binary classification. Our data is in R5. This would be the original tree that we would learn if we looked at the entire data set and learned it on the original data set. But if we first resample from our data set n times and learn a tree, this would be, for example, the first tree we learned, the second tree, the third tree, up to the 11th tree. And so the reason that each tree is different is because they're learned on different data sets. Each individual data set contains our original data in it, but some are duplicated and some don't appear at all. So these are 11 different views of our data set, which would give us 11 different trees. Each one of these trees doesn't have to be great, but their combination is suddenly going to improve the overall prediction. So we can see that when we go from one tree up to, say, 25 trees, using these bootstrap samples, we get a clear improvement, but then at a certain point, the improvement stops. So that says that at a certain point, bagging more trees is not going to improve our classifier at all. However, as described, there is a certain limit to the performance, and in general, the reason is because each of these trees that we learn is highly correlated with each previous tree. And so that's why we suddenly need two different trees. So the way that we can reduce correlation is by making a simple modification. We still bootstrap our data set multiple times. We still learn a tree on each bootstrapped data set, except when we decide whether we want to split a region, rather than looking at the entire bootstrap data set, looking at all of the dimensions, we're going to randomly subsample a set of dimensions and only make each partition along one of those dimensions. So this leads to the final algorithm called random forests. As an input, we have something called m, which is a positive integer. This is the number of dimensions that we're going to consider on each split. In general, m is going to be less than d. Often we set m to be about equal to the square root of d. Then, for each value of b, we first generate a bootstrap sample from our data set of the same size as the data set. So we sample our data set to construct this bootstrap sample. We then train a tree classifier on that bootstrap data set. But now we compute our splits as follows. First, when we decide that we want to make another split, we randomly select m dimensions from the original d dimensions, totally at random. And we do this for each b. We then make the best split restricted to only that subset of dimensions. So each tree is only going to consider a small subset of all of the dimensions in our data set. And then that's the final classifier. So the difference between bagging of these trees and random forests is that when we bag trees, each tree that we learn on the Bootstrap data set uses the original algorithm we discussed, whereas with the random forests, we also bag trees, but each tree is now learned on only a random subset of the original d dimensions. And so what this is going to do is break down the correlations between the trees that we learn. Here's the final result of what we get with learning a random forest on this binary classification problem. What we did was we learned about a few hundred trees from a few hundred bootstrapped data sets. And then each tree is going to make its prediction of either an orange or a blue class. We let each tree make its prediction, and then we take the majority vote of these few hundred trees to make the final prediction. And we can get these decision boundaries. So for example, all of the data in this region will have the majority vote of all of these trees say orange, and all of the data in the blue shaded region will have the majority vote say blue. But notice that we can learn some quite complicated decision boundaries. However, because our trees are splitting along the two dimensions, they tend to align, the decision boundaries tend to naturally align with the two dimensions.